welcome. We will continue multiple linear regression. Today I will talk about the model adequacy test primarily, whether regression equation is adequate or not from the data or the experimental data you obtain that basically have given you a proper response surface or not. So, first we will start with the overall hypothesis testing using F test, then I will give you some goodness of fit test measure like R square, adjusted R square. Test of individual parameters we will revisit, because earlier I have shown you how to do, and another important one is the test of assumptions. So, when I talk about test of assumption, I will give you the what are the assumptions and how those assumptions must be verified that they are really true. So, straight away let us go to that regression equation here, that y equal to x beta plus epsilon. Now, if you when you estimate the y, it will be y equal to x beta cap, and all of you know then in scalar notation we can write like this, and ultimately the difference between the actual observation minus the predicted one, or other way I can say fitted one, is the residual. So, ei is yi minus yi cap. So, as there are n number of y values, so that means there will be n number of residuals. So, in matrix form, then that E equal to y minus y cap, it is a n cross 1 vector, and if we just do certain level of manipulation for E, we will find out that E will be I minus H into y, where H is x transpose x inverse x transpose. So, we can see that the residual can be written like this, I minus H into y, where I is the identity matrix and H is known as hat matrix. H is known as hat matrix, which is x transpose x inverse x transpose. This is the part. Okay. It's a very interesting matrix, because it has lot of implications. It can be used for doing lot of tests, particularly if suppose we are interested to know what are the contribution of individual observations. That time you will find out that the diagonal element of hat matrix will talk about the contribution of individual observations. Suppose you have n number of observations, diagonal element will talk all these things. Okay. So, anyhow, let us see one data example. We have 16 observations. We have two factors, x temperature and catalyst feed rate, and our dependent variable is viscosity, that is to be predicted, let it be, and we have fitted the model, and which we have already shown you earlier, and then from there this model we found out the predicted values or the fitted values here, exactly these are fitted values. Then this viscosity observed values minus fitted values is giving you the residuals, these residuals E values. This is the last column. Now, what we will do here, we will actually the one of the important assumptions here is that the errors are normally distributed, identical and normally distributed, IID, independent and identically distributed, and that is also normally distributed, that is one. Okay. So, anyhow that test we will see later on, but what is the hypothesis overall fit test here? Overall fit test is that we have j equal to 0, 1 to k, that means k plus 1 regressors. If we do not consider this one, that the intercept, that beta 0, then we have k regressors, and that means beta 1, beta 2, like this beta k, and that is important, because beta 1 related to variable x1, x2 and xk, like this is important, which of the variables are contributing or not. So, here what we will do, we will for overall test we say that beta j not equal to 0, that means none of the factors are contributing towards the response what we observed during experiment, and H1 is beta j not equal to 0 for at least one beta j. That means at least beta 1 or beta 2 or beta 3 some is contributing, and not that all beta j are 0. This is overall test. This overall test is done through F statistics. You have seen in ANOVA that sum square total equal to sum square I think the treatment plus sum square error in one way ANOVA. You have seen this one. Here also in regression we can write sum square total equal to sum square regression plus sum square error. This is sum square regression, or we can say that is sum square model. Okay. And all of you know that y transpose y will give you this, and sum square regression will be that beta cap transpose x transpose y from this, and essentially then AC will be SST minus SSR, which is will be y SSE will be y transpose y minus beta cap transpose x transpose y. This will give you the SSE. Okay. So, fine, then SSR also beta, that is okay. Then finally, what happened? Okay, I have given probably little difficult equation differently. Let us see that SST all of we know will be this following these equations. So, here y transpose y, when it is mean subtracted is there, that time if you subtract by y is mean subtracted, that is formula, but otherwise what happen, SST yi square minus this, that means this quantity is coming here. Similarly, SSR also, that this will be subtracted, and SSE, then this SSE is y transpose y minus this, and SST equal to y transpose y minus this by n, y transpose y minus yi square by n. That is what we have seen. It's a basically some kind of duplications we have made, but whatever may be the thing, you please remember you will be able to compute SSR, you will be able to compute SST, and SSE also you will be able to compute from errors residuals, but other way SST minus SSR will give you SSE. So, then what happen, you will create a statistics called F0. This is nothing but SSR divided by K by SSE divided by its degree of freedom n minus k minus 1. So, if this one is greater than f k n minus k minus 1 may be alpha. Okay. So, then what we will say, the H0 is rejected. H0 is rejected. Now, what is this SSR by K? This is MSR. What is SSB by degree of freedom? MSE. So, that means MSR by MSE, if it is greater than k n minus k minus 1 alpha, will this F0 is this, and then we will say that the null hypothesis is that none of the factors are contributing is not correct. This is what is in terms of ANOVA table. If you see the ANOVA table here, it is in terms of ANOVA table, we have shown the same thing. Okay. So, this is overall F test. Overall F test will say that whether at least one of the regression coefficient contributing or not. If none of the regression coefficient is significant, or none of the factors x variables are contributing, then that is what H0 will be accepted and none will be nothing, no influence. But what happened, we may be interested to know that suppose F test is says that H0 is rejected, then we want to know, okay, that what is the variability of y is explained by x. Suppose this is, if I say the y variability, maybe the regression y is x beta plus epsilon, then this x beta, this portion may be able to explain this much. So, what is this portion? So, this portion it is some kind of absolute measure that the variability of y explained by the regression model that is divided by the variability not explained by the regression model, or total variability will give you a measure which is known as R square. So, R square is a measure which is SSR by SST, that means variability explained by the model and total variability of y. Variability of y explained by the model and total variability, this is R square. This one can be written like this, 1 minus SSE by SST also. Okay. So, what is the problem here? Problem is, if I expand this, I can write what is SSE, we can write that SSR by SST and SSE by this one. So, we can write like this, SSE by n minus p by SST by n minus 1, where p equal to k plus 1. If you write like this, then this quantity will give you a measure which is known as, suppose this quantity gives you a measure which is known as R square adjusted. Okay. So, I will explain little further this one. So, R square I can write 1 minus SSE is nothing but n minus k minus 1 into AC square. You have seen earlier AC square. Similarly, SST you have seen n minus 1 into SY square. So, now if you divide the thing this by degrees of freedom n minus k minus 1 or n minus p, and this by its degrees of freedom, you are getting this one. So, we are creating another coefficient fit measure R adjusted R square, which will become then what happen, R S square if I write, then this will be SSE by n minus p means n minus k minus 1, that means this is AC square. SST means n minus 1 y square by n minus 1 means SY square. So, this portion, this value is, this R square value is unaffected by n and p, that is the sample size as well as the parameters, number of parameters to regression coefficient to be estimated. So, it is irrespective of sample size, this value will get, and it is a better measure than R square. R square will be inflated. Suppose n equal to p, then this quantity what happen ultimately, this quantity will become, for example, here if I write n equal to p, this will become 0. So, R square become 1 means abnormally high R square value you will get. So, and okay, whatever may be the case, R square will lie in between 0 to 1 and R A square also lie in between 0 to 1, and R A square is greater than equal to R square. This R square is, that is coefficient of multiple determination. Okay. So, this is the goodness of test. If R square value is greater than, in case of laboratory experiment, whether R square or R A square, if it is greater than equal to 0.90, then it is a fit data, is a good fit to the model, regression model. Okay. So, fine, you just see that multiple R square value, that 0.96, okay, I think R square SSB by SSR by SST, fine. So, R square value 0.92, adjusted R square 0.91, and standard error is 16.35, observation 60. Okay. So, R square and adjusted R square both are more than 0.9. So, we can say that it is good, that the data is fit to the regression model. this is the F test what I explained to you. Now, F value computed 82 and it is highly significant. That means what happened, model the predictors of the factors are contributing. Individual parameter test earlier I have shown you, and here this example is repeated. Now, now the test of assumptions. Test of assumption is very important in regression. What are the assumption? Multiple linear regression. One is the linearity, normality, 3 is your constant variance, 4 is IID, independent in nature. I can say independent or uncorrelated observations. Independent or uncorrelated observations. So, from residuals plot we will be able to find all those things. Residual plot will help you in knowing that whether they are valid or not. Anyhow, let us see that for this data set we have found out the residuals. This is temperature versus residual. You see the residual plot here. Now, in case of linearity we have shown here partial residual plot. This is residual versus x1, that means this versus this, and we do not find any pattern here. Okay. But when you go for partial residual plot, that means the residual plus the x1 contribution and versus x1, then you see that a linear plot is obtained. So, that means linearly related. Now, similarly for x2, but this linearity is your little weak, because that is more spread. Okay. Now, second one is that here I am showing that heteroscedasticity it is nothing but that error variance are not constant over x. If you recall my first lecture, I say if it is x and this is y, suppose we are fitting a regression line when we are having only one predictor variables or factors, then we say that for every fixed observations, suppose this is x1, this is xi and this may be xn, every fixed observation, if I keep x at x1 and do experiment several times, I may get y like this, y distribution like this here, y distribution like this here. The assumption is that irrespective of your x value, the y variability across x will be same or constant variance across the x. This is known as homoscedasticity. If there is violation like this, when x is low, like the value is like this, f is high like this, and this is high like this, or other way around. So, this one is big one, or other way around. So, this is the biggest one, this is what is this, and this is what is this. So, then you will have either funnel to left or a funnel to right, this kind of situation. Then this is a situation for heteroscedasticity, not unconstant error variance across y, and this is a violation of constant variance, and regression estimates will be inflated or it will be wrong. That is the issue. Okay. So, if you how to know that it is happening? So, if you plot the residual value versus predicted value and found some kind of funneling effect, then it is a heteroscedasticity problem. But if it is random, then it is not. Okay. So, for uncorrelated errors or independent, suppose the order in which you have done the experimentation, put this side, and residual in the vertical y side. So, then you see that whether these observations are showing any, it is a random observations, there is no systematic pattern in the plot, then it is uncorrelated. So, and what about the linearity, normality part? I think I have told you PP plot, probability plot earlier. So, for all residuals you do this residuals use for PPT plot, QQ plot, or also you can say individual Z test. Suppose Z test of highest error, highest residual, Z test of highest residual, maximum residual. So, you just find out the maximum residual E max from this data, and then you divide it by your error variance, that is MAC, and if this is greater than suppose Z 0.025, then we can say that there is the violation of normality. Okay. So, for uncorrelated errors there is another test called Durbin-Watson test, and here what happened, just to see that whether the errors are correlated or not, you take the error in this order, and you create some lag, maybe 1 lag or some lag, that 1 lag, 2 lag, k lag maybe, and then you find out the correlation between the two. And here what happened, this is basically the residuals, and we created the I minus 1 and EI. This then we have used this formula and found out the R value, and it is shown that the R value is minus 3.33 and Darwin-Watson test value is 2.65. It is correlated, but 0.3 is significant, I think, because it is not less. Again, R square, the Darwin-Watson value is also more than 2. Okay, but it can be considered other way also, because it is also R square and other things giving you better value. But this is one assumption which is supposed to be violated here, because the constant error, independent part. Okay. Now, I talked to you about normality, and this you know this normality. Earlier I have shown that the residual, that you use the normal probability plot, and if there is a straight line kind of things, and this I minus 0.5 by n, if you use this formula you will get a straight line, that is normal. There is another one is that residual versus Z score, means quantile plot. This quantile plot is also showing some kind of normality. It is not deviating from normality much. Okay. Last but very important one also, that means what happened when the constant error variance as well as normality assumption is violated, you have to transform the data. So, there are many methods of data transformation, and please remember this homoscedasticity, it is a feature for the dependent variable y. We are talking about fixed effect model, and x are fixed. Okay. So, when you talk about transformation, so it is primarily related to y, but sometimes many times we also do x transformation, so that the relationship can be changed. Some of the assumptions can be satisfied, for example linearity, for example maybe normality also. Okay. So, here what I will show you very quickly some of the methods for transformation. One is Box-Cox method, and another one is, I think some more methods are there, but primarily we will be considering on Box-Cox. If there is heteroscedasticity, then you transform y using Box-Cox method. If there is a linearity, you can transform y, x, or both, it will help you. If it is normality, again go for Box-Cox method. And this is what is the transformation kind of thing. Suppose you if constant error variance is satisfied, there is no transformation required. but if the error variance is proportional to the mean value, then find out take the square root. If error variance is proportional to mean and this quantity, then make sine inverse square root transformation. If it is square of mean, log transformation. If it is cube of mean, then inverse square root transformation. If it is fourth power mean, then you do 1 by y, that is inverse of this. These are some guidelines you can use while you do some kind of analytics, that is experimental data analysis. So, you see that although this kind of transformation will give you the desired result, and this is available in Montgomery linear statistical models. So, you see that if the function is something like this, then you go for log transformation. Function like this, go for this. Function like this, go for distributive transformation. And you do not know which transformation will help you, but that is why what happened, you may do all kind of transformation and then find out that whether the assumptions are satisfied, particularly in the linearity point of view here. And you do Box-Cox transformation for normality and heteroscedasticity. Here what happened, you basically create a power lambda, and this you are creating another normal variable y to the power within bracket lambda, which is y to the power lambda minus 1 by lambda into y dot lambda to the minus 1. Now, the lambda obviously not equal to 0 in the first case. If lambda equal to 0, you write y dot log y, where y dot is inverse log 1 by n I equal to 1 to n log y I. That means, you take the log of the original observations, then take their sum, divide it by their take the average of log transformed information, and then its inverse, log inverse. So, you choose, and this is basically y dot, and now you choose different lambda values, feed the regression equation y equal to x beta plus epsilon, calculate SSE, and then plot. So, what happened, you will choose lambda, different lambda value like this, then your y equal to x beta plus epsilon, some model will be there, and then you will calculate SSE, some value you will get SSE, and then you plot lambda versus SSE. What will happen, you will find out a curve like this, where this lambda is giving you the minimum SSE value. This lambda, this is lambda star. This is the best transformation for you. Okay. So, choose lambda for which lambda SSE lambda is the minimum, and now again fine, that equation is also known, you know which lambda is minimum and equation is known, and that linear equation you will use. Okay. So, so let me just do one, let me summarize the thing. We talk about regression, and primarily it is linear regression, and in linear regression, and obviously we have two sets of variable, dependent variable 1, independent variable several. We are interested to find an equation like this, where epsilon is the error term. We have estimated beta using certain equation, and then we have estimated the mean value and the variance of beta. Then what we have tested beta, beta j equal to 0, H0 beta j equal to 0, beta j not equal to 0. We also found out the 100 into 1 minus alpha % confidence interval for beta j, that also we have found out. And then also we found out that whether the model is fit or not using F test, overall F test, and your R square, R A square, and then Also, we have discussed that a H0 a set of variables contributing or not contributing, both partial marginal test and subset hypothesis testing we have done. And then we have gone for test of assumptions, both linearity, normality, homoscedasticity, independence, all those things. And we have also seen some of the examples, particularly here we using two independent variables and one dependent variable, and how this model is working or not. Nutshell, what I mean to say, you must know that the data fit to this model. You must know that every model has certain assumptions, those assumptions must be tested. You must be aware that when you are saying a model, that model must be fit to the data, that is the adequacy test, overall fit test. When the overall model is fit, then you go for individual parameters, whether individually they are contributing or not, and accordingly you accept or discard those variables which are not contributing. Again you rebuild the model with the significant parameters. You may find out some of the estimates are different than the earlier. If that is the case, you please be careful. If some of the variables become insignificant, then there may be the partial correlation, there may be problem in, from the beginning, data collection to or variable selection to maybe the test and test of assumptions and all those things. So, thank you very much. Again I must tell you that the Montgomery book and my earlier NPTEL video lecture on multivariate statistical modeling. Thanks a lot. Thank you very much.